All right, so we're going to talk about ensembles. In fact, you already learned some ensembling, okay? But let's just say it was motivated a long time ago by the idea that great minds think not so alike, okay? Alike, but not enough that it's not useful, okay? So you may have heard of this thing called the Netflix Prize. In fact, we talked about it in our the very first lecture, right? When we're talking about paradigms of machine learning. They are, you already know Netflix. It was originally a DVD distribution by mail. I don't think many of you use DVDs anymore, but except maybe for PlayStations and stuff like that. But the whole point was that you would actually get a DVD in the mail, and then it would recommend which things that you could borrow, and then you could keep the DVD for however long you wanted. Okay, and then Netflix had this competition to improve its recommendation process because it wanted obviously to have more people watching movies and being stuck on its platform so it could make revenue. Okay, so they offered $1 million US dollars, so it's like 1.4 or whatever, 1.5 here, uh, to any person or the number of groups of teams that was able to improve the performance of its recommendation system by 10%. Okay, so actually, the top couple of teams after the first couple of weeks already did pretty good. Okay, so they are already see, you can see over here, already got performance that's not bad, about 5 points better than before the basic algorithm. Okay, but after a while, after the first couple of weeks, they all stuck around here at zero point 0.5. Things tailed off. They didn't get that much better. Okay, so you can see there's a big plateau here. Nothing got that much better. Okay, they want to reach this part, okay, where there's a 10% improvement, then they win the $1 million. Okay, so people got desperate. They said, okay, I don't know how to do this problem, but you got a pretty good solution. I got a pretty good solution. Why don't we work together, right? So that's the idea of an ensemble, right? So this team rookies is basically a collaboration, right? So they took a team and they worked with this other team called Paul Harrison. I guess the person who's the data scientist there, his name is Paul Harrison, I guess. All right, and they came up with a new algorithm, okay, that improved their mix, okay, to 0.675. I guess Paul then cloned that solution because it says here the two solutions are exactly the same in performance. Okay, here's another gentleman, Eric Paterick. My approach is to combine the results of many methods, also the two-way interactions between them, think covariance, okay? And using linear regression on the test set, the best ensemble is regularized SVD. SVD you'll learn in next week, okay? Or this week if you're watching the lectures, with biases, post-process with kernel-rich regression. So we know rich regression already. That's our linear regression with L1, L2 penalties. Okay, and then we get a score of 0.762, not bad. Okay, and then people got not so creative with their names, right? So you have a team here called Gravity and another one called Dinosaur Planet, and they made a new one that's called When Gravity and Dinosaurs Unite. Okay, so they got slightly better performance. Okay, 0.838 on the actual chart. Okay, and they blended it together. So actually the one team that won this contest is actually this ensemble, okay? So you can see it here. This is in the history books now at this point, okay? So they had Belcore, which had 2 people, 3 people. Some of them are well known in the machine learning community, and another couple of people from pragmatic theory and another 2 people from big chaos. So basically like 8 people teamed up with 3 different algorithms and put together a nice ensemble of a name too called Belcore's pragmatic chaos, right? And then they came up with an algorithm that actually beat the improvement, okay, 10%, and they were awarded $1 million. Not bad for doing data science, right? Okay, so of course, now $1 million doesn't go so far because GPUs cost a lot to train, but yeah, I'm just making a joke. Anyways, the idea is that, you have the quality of individual algorithms and then finding a good way to put them together to get a good ensemble, to get the right trade-off between diversity and accuracy. Okay, so ensembling you already have experienced, right? When you did neural networks, what were you doing? Every time you stacked a layer on top of another layer, that is an ensemble because you took units from bottom that represent primitive features that were already combining the raw features and then ensembling them together. Okay, so basically we can create an ensemble out of individual features or classifiers acting as features, right? So let's say we are doing something like stock market prediction because you don't want to pay your college tuition for the rest of your life. You want to pay it off right away. So I'm going to bet on the stock market. I'm going to create a bunch of ensembles. Okay, either I use machine learning and create my own algorithms, or I go to reputable people, my parents or a stockbroker, etc., and I ask them for their opinion, okay, about a particular stock. And I'm going to say that particular stock is, I ask them about that. They get to tell me a binary answer, yes or no. Okay. And then I'm going to make my investments based on this basket of experts. Okay. So there are a couple of different ways that we can do, right? We can trust which one is the most trustworthy based on their usual performance, right? So this is the idea of validation, right? I'm going to minimize, right, my validation performance, right? So I just look at this part here, right? I choose the one that has the lowest validation loss, okay? And then I'm going to pick that guy to be the winner. So I'm looking at all of the other predictions that that person made, okay? And then saying, okay, you have picked the best overall for the entire time period. I want to know what you think. I'm going to do what you think. Okay, you can be more democratic and say everyone has a uniform chance of influencing. Your vote matters, right? So I'm going to do it this way. Okay, so Ching Han writes, should top N be candidates of the ensemble or most diversified, not necessarily be top ones be a candidate? That depends. Okay, that depends on what you're using for your ensemble criteria. Here we're just saying we have a number of different predictors, right? So if we want, we would try to choose some things that have some diversity to them. And we're not going to quantify it too much yet. So that's a good question. We can come back to that in a little bit. Certainly, you're right to say if I have an ensemble of 500 students that all do the exact same thing all the time, they follow the lecturer's instructions to the T, and only know what they're supposed to learn, then having all 500 students is as good as having one student, right? So we want some type of diversity in the ensemble network. Okay. Yeah, you're welcome. So then if we want to do something else, like let's say measure like what Ching Han said, how interesting are you as a candidate? Okay, how rare or how much alpha or beta or whatever you want to say in terms of stock market on terminology uh, are are your reports. Okay, so if I know your reports are generally good, maybe I trust you more. This is the idea that we already saw in Ada Boost. Okay, when we went to that, I'll cover it again. Don't worry. Okay, and we could do weighted ensembles, right? So I just say, democracy is for dummies that are Trump supporters. I want to say smart people who are scientists should have a higher weight. Okay, that's going to get me in hot water. Okay, but don't repeat that. Anyways, the whole idea is that you have certain experts and you're going to trust their judgment more. Okay, so that's the idea. Okay, you can also decide to do combine them conditionally. I can say if T1, stockbroker number one says yes, then I'm going to ask T2 and T3 what they think. Okay, and we actually did this. This is our decision trees, right? And the basic idea of this type of conditional learner is the decision stump. Okay, we learned the decision tree, which builds a whole tree, but the whole idea is that when you have this choose attribute test, right, you can engineer a decision stump, right? Basically, throw away the decision tree learning algorithm, just choose the most valuable attribute and use that to decide what to do. Okay, There are other things that we've done. Okay, so you can think about what type of algorithm you learned in the deep learning lectures, right? In the neural network lectures, they're basically doing what? They're doing stacking, which is a type of blending. Okay, to take all of these different things together and then blending them using coefficients, right? And then aggregating them. Okay, and like Chinghan already mentioned, for us, the key is that the component hypotheses need to be diverse. So it's nice, and it's usually some type of criteria that we want them to make different types of errors, different types of correct judgments, right? Okay, so when we want to think about taking a single learner and making a diverse set of learners, one thing we can do is play with the data set itself, okay? So if you recall the idea that we had some like big data set, okay, and we cut it up into parts, okay? And we can do something like take one part of it, okay, and treat it as training, okay, and take the other parts of it and treat it as test. Okay. Maybe we use the yellow as training, okay? Then what we can do is we can rotate this around, right? And the whole idea is that each of time we look at the training data, somehow it's similar, but not exactly identical. And what we want to do is we want to train different learners from this, right? So what we're going to do is think about manufacturing more data than is observed in our M samples. Well, that seems crazy, right? We are only limited to M data points. How could you make more? Okay, well, we can. What we're going to do is you're going to use a statistical technique. It's called bootstrapping, okay? So it's very similar to what you may have done yourself when we talk about augmenting your data set, okay? If you do CNN or RNN type of work in your projects and you did deep learning, this whole idea comes from the idea of bootstrapping, okay? Making sure that you have your data set and trying to enlarge it in some way that makes sense, okay? So you can cover more signal so that your generalized your learner can generalize. Okay, so we're going to learn one that's called bagging. So bagging is actually a terrible name. I hate it because it's actually an acronym, right? It's bootstrap aggregation. Okay, so bagging just means that we're going to construct multiple bootstrap samples. How do we do that? Bootstrapping means basically what it says here. Okay, it says we're going to take the data set, put it in a bag. Okay, so that's a pun. Okay, I don't think that's intentional. All right, put it in a bag and then pull out with replacement. So take it out and see, okay, number 41, put it back in, take it out again, number 38, put it back in, okay? And then sample the same size data set, all M examples, okay, one time, okay? But we know how to do it one time, right? We can do this resampling process as many times as we want, okay? So let's just say I do this process T times, okay? I'm gonna go from 1 to T. I'm gonna ask my bingo player to draw out M size data points, okay, with replacement. Because if I don't do replacement, obviously I get back the same data set, right? So I do it with replacement. And then I'm going to ask all of these data sets that I've just drawn, which are very, very similar to each other, right? They're just different in how many times a particular sample was picked, sometimes 0, sometimes more than 1, okay? And then I'm gonna ask a learner to go learn on it, okay? And then what I can do is then say, okay, I don't care which of these are more trustworthy than the other. I'm just going to take a uniform, random, uniform voting of all of these guys, okay? So that's very simple, right? I just aggregate, bootstrap aggregate, sample with replacement. This gets us a nice normal distribution from our data set. If the data samples are big enough, I obtain the learner, the learn algorithm from this, and I just ask them to uniformly vote. Okay, so it actually works pretty well. So here we have Perceptron learning algorithm, what we learned in week 3, okay, and a very, very simple algorithm. You can see a lot of the decision planes here didn't have a bias weight because they all went through the center. But basically here, when we do the voting, you can see that we get a broken line segment type of boundary, right? Because when all of the classifiers, the majority of the classifiers votes for a boundary, then that line segment is in the boundary. Okay, so bagging works reasonably if the algorithm is sensitive to data randomness. So it has to have some high variance, right? So if there's enough variance in the algorithm, then that will work. If we choose a classifier like an H0 classifier, okay, there's not enough power there. It's going to have a very heavy bias error, not enough variance error. So even if you bag a H0 classifier, you're not going to get anywhere. Okay, so that's why sometimes having good high variance classifiers is a good thing, right? Because when you ensemble it, the whole point is like you have a different perspective, right? Okay, you have an opinion. Can we say it that way? Okay, so what happens when we bootstrap? Okay, what happens is on average, when we have a large data set, we get about 60% of the examples from the original data set appearing in our data set. Okay, that's what happens when we sample with replacement. Okay, because you can just do the geometric series here. Okay, as it says over there. Okay, you can look it up in the math. All right, and then you will find out that when you draw with replacement and you sample the same size, okay, then you will get about 2/3 of the instances inside the data set. 1/3 are all going to be duplicates that are obviously one of the ones that you picked out from before. Okay, so if you've done enough sampling, actually the entire classifier, because it's voting all over all of the data points, will actually have seen all the data points. But each individual classifier is trained with significantly less data, right? So this is an artificial way of getting an interesting, diverse sample, right? Because if I only give you 60% of the data, and I ask you to train a classifier and I give your classmate another 60%, but not necessarily the same ones, okay, probably different, then you might learn different things, okay? So I take the uniform averaging of all of this and hope that is one way to overcome, having too much power, generalization power, okay? So like it says here, because it appears in 60% of the data points here, on average, an example will be in the majority of the bootstrap samples. Okay, so yeah. So we're gonna get to this concept of out of bag, okay? So out of bag just means, like it says here, hold on a second, stopping this room. Okay, and what we're going to do is look at a particular set of examples. So I have examples 1 through m here in my data set, right? Okay, so I have m examples, right? And what I'm going to do is I'm going to ask myself, did I get to look at this particular data item when I trained the classifier at round whatever, or round t? Okay, so in the first round, I happened to pick um, example 1. I also happened to pick example n, but I didn't get a chance when I was sampling with replacement. I didn't see x2 and x3. Okay, right? When I did the second round, I didn't actually see 1 and 2, but I saw number 3 and I saw the last example. Okay, and I can do this so on and so forth. Okay, and basically the idea is that you can see there are different classifiers are exposed to um, different data points, right? So we already said that if there are 63% of the examples that are actually sampled in the data set when it's large enough, in the limit of large numbers, then that means the out of bag size, meaning the ones that we didn't see, is approximately 1/3, right? And what we want to do is basically use that 1/3 to validate that hypothesis, right? We're going to just say, okay, you trained on these guys over here. Okay, you trained on these guys over here. Now I'm going to test you with the guys you didn't see, okay? And then I'm going to see how well you do that, right? This is called our um, out of bag error, okay? So it's just a formula as you can see there. I'm just going to take all the points that I didn't see, okay, that I didn't see, and then use that to determine the bag the out of bag that I can test on, right? I can't test on the ones that I've actually seen because that would be unfair. That's a violation of train test separation. Okay, now I want you to step back for a second. You know another algorithm like this from week 6. It's called validation. It has a very similar but distinct difference between out of bag. Okay, you can see it in this diagram, right? We just talked about out of bag on the top, right? Out of bag looks like this, where each particular hypothesis has a different view of the data set. Okay, in validation, that's not what we're doing at all. Actually, that would be a terrible idea for validation, because we want to compare like to like apples in validation. Because what are we doing with validation? We're picking the best hypothesis based on the training data. Okay, so that is one thing that we're doing there. Okay, so sorry, let me take a look at some questions that you guys had. So cross validation, cross validation is going to be similar to this, but you'll have this section at the bottom, okay, repeated many times, right? Because your validation data might be switched to other roles, right? Okay. But the key point here is that when we do validation or cross validation, we want to keep all of the training samples and all the validation samples identical across all of the classifiers, because we are trying to do one particular thing, okay, when we validate, which is choose, min j train, right? Or sorry, j val, okay? All right, this is the optimistic part that we talked about in that lecture, right? That we're using this performance to choose something. It's on our validation data. It's not actually on our test data. We never get to see the test. So it's going to be optimistic bias, okay? But in out of bag or in this in our bootstrapping, that's not our goal at all, right? The goal is to combine these together, not to choose among them. And the whole point of combining them is to say you want to have hypotheses, like Ching Han said earlier, that are diverse. Okay, we want to benefit from diversity. So irrespective of what we can say about diversity in the workplace or whatever, diversity is also very important for machine learning. Okay, so I happen to be a big fan of diversity. I come from states where that matters a lot more, and I have to say it's important in machine learning too. Okay, so when we think about bootstrapping, what it is really doing is, if you think about it, it's basically doing the same as what we talked about in Ada Boost. Okay, we haven't covered Ada Boost yet, but we talked about it a little bit before. The idea is that it's taking the data set and telling you which examples are important and which examples are not. Okay, so if you can say we started off with a data set like this, 1, 2, 3, 4. Okay, when we did Bootstrap, we happened to sample 2 of 1 and no of 3. Okay, so 3 went bye-bye. So this one went away, right? So we have no 3. Okay, and so what we can think about is that we ended up with a data set where the weights are like this. Okay, all right, so we can say we are going to assign unequal weights to all of the data set, right? We're going to do it through this coefficient u of j, okay? And we're just telling you, okay, when I resample at Bootstrap, I'm giving you a non-uniform weight assignment for all the instances. Some instances, the 37%, 36% that don't appear, they're gone, right? They're wasted. Bye. Okay, but the other ones might be upsampled, right? Like this one over here. Okay, we like you, we sampled you twice. Okay, so you can think of it on the Bootstrap data set, right? So it's the same here, right? We're basically observing 2 instances of that, 1 instance of number 2, 1 instance of number 4. And here we're just uniformly weighting, right? Because we've got 4 instances. We don't have this u of j, okay? But it's basically the same, okay? These two are equivalent to each other, right? We can think of these two as the same. Okay, so you got the idea behind this, right? Is that we can think about bootstrapping as a nice, simple way of taking weights and playing around with them. Okay, so the set of hypotheses that we get from using a simple ensembling, where we just combine all of the classifiers by uniform, without confidence, okay, is diverse, okay, because we have this resampling procedure. Okay. Now, as you might be thinking, the whole point of this is to reduce our error on variance, okay? Because we're not taking any one of these classifiers that is sort of like brain damaged. By brain damaged, I mean we're not training on our whole set of neurons or instances here, right? We only took 60% of the training data and even reweighted it so that some of them are more important than others, okay? And then decided to train on that. Okay, so it's going to have higher variance, but then we're going to reduce it by averaging over that, right? The important thing is that even though we're reducing our variance error, okay, we actually don't get a big increase in bias because just like we saw in the bagged PLA case, we're actually working with the whole spectrum. We have many different line segments we're adding together. Okay, so actually this helps a lot, okay, having simple classifiers. This is why I tell you that the linear models are so important, okay, simple classifiers and combining them in slightly interesting ways, okay, so bagging is one of them, actually gets us a good idea of how to learn, okay. So could we do something better? Can we do some more simplified H for learning ensembles, okay? Do we have to use something like PLA? Right? And you already know the answer to that, right? Because the answer is Ada Boost, right? So we've already talked about this a bit. Okay, the whole point is that you have a decision stump, right? You're choosing the most simple classifier. Choose an attribute, choose a threshold, choose a direction. Okay, so I choose an attribute x1. Oops, go away. One, yeah, all right. Choose an attribute, I choose a threshold, and I choose a direction, okay? Those three things characterize the decision stump, okay? And all I'm going to do with that is I'm going to do the same thing as what we did in bagging, right? The key difference between bagging, okay, and boosting is coming from its name, right? Boost means to upgrade, right? So now we're not going to use a uniform weight, right? We're going to change it and we're going to say confidence weighted. Okay, that's the idea, right? Because like when we are calculating the decision stump, we need to know what's its misclassification rate. That's going to tell us our alpha for that particular guy, and that's going to help us decide for a data set that was positive, meaning correctly classified, and an example that was incorrectly classified. Okay, what to do with it, upweighted or downweighted, right? The positive ones get downweighted, negative ones get upweighted. Okay. All right. So we're now at the final part of the lecture, and I think we're doing pretty good on time, which is really cool. I like this algorithm a lot. It's called random forest. Okay, because it embodies the best of both worlds. So you get, you get to have your cake and eat it too. All right. So we already taught bagging, right? Bagging is really simple. You say you bootstrap a whole bunch of data sets, as many as you want. You do it T times. Okay. Then after that, you build some classifiers and then you weight them, right, uniformly. Okay. And you can see here, the bottom line is it does something really cool because it reduces the variance by averaging. Okay. Now, if you look at decision trees, on the other hand, they have a different type of problem. Okay, if you look at how it works, you end up with a large variance. Okay, especially if you choose attributes based on bagging, right? Because when you have different data points, you're going to get very different types of decision trees. We already told you that it's very sensitive to the data that's put in because it can grow a tree that's going to have training loss of 0 because as long as the data set's not noisy. Okay. So we want to do two things at once. we want to use a decision tree, which is already an ensemble, right? It's an ensemble of decision stumps, but done conditionally, right? Because it has this if statement, right? Okay. So instead of doing that, what we're going to use bagging on it as well. Okay. So the idea of a random forest is to use a forest. Well, a forest is just a bunch of trees, right? So I'm going to run the decision tree learning algorithm several times, right? Okay, as many times as I want, maybe t times, okay, to get a forest, okay? So this is what a random forest does, right? We're going to go bootstrap a bunch of trees, right? I'm gonna return them, okay? And that is this random forest algorithm. Well, not quite. Okay, that's the easy thing. This is just bagging decision trees. Okay, we haven't done the cool thing, which is random forest later. Okay, but you can get the idea. It's like, okay, we have something that has high variance, which is our decision tree algorithm, and so I couple it with something that's also going to produce high variance, which is the idea of doing bootstrapping. Okay, so I bag a lot of things, right? And then it's nice because obviously here I can do this quite efficiently. I can generate the samples in parallel. Then I can say for each processor, go run decision tree learning algorithm. Then, when I have a data instance, I send it to all of the trees. They all classify. I get back an idea, and then I come out. Okay, but the key point is that a random forest is just not just bagging decision trees. If it was that, they would have called it bagging decision trees, okay, but it's not. Okay, they have one other cool trick up the sleeve, and this is diversifying by feature projection. Okay, so right now we have been talking about diversifying what? Diversifying our data instances, okay? Picking whether you want to look at instance 1, instance 2, instance M, right? That's what we did, okay? But now we're going to also think about another part, right? Because what we were doing before is looking at this big data matrix and saying, okay, which of these lines do I want to sample, okay? That's what we were talking about, okay? Now we're going to think about the other axis. I'm going to think, which of these lines do we want to sample, okay? Each of those lines is a feature, right? We talked about that in decision trees. We want to pick the feature that's the most interesting to split on, okay? What we're now going to do is the same thing. We can choose how many features we are going to give to the classifier to look at. Okay, so for example, a particular decision tree might just say, okay, well, I only allow you to look at these 4 columns, okay? And that's going to be decision tree number 1, okay? Decision tree number 2, you only get to look at these guys, okay? You make a decision tree based on that, you tell me your answer, okay? And decision tree number 3, you get to look at these columns here, okay? You only get to look at that, you make a decision, okay? So that's the idea of this nifty thing called feature protection, okay? So between bootstrapping or bagging, which is choosing your instances, okay, and feature projection, which is choosing your columns, we have 2 different ways to diversify the data set. Isn't that cool? It's both axes, okay? So we can choose the same thing. We could do, sample with replacement, but normally we don't do that here. We just do something a bit simpler. We just say choose some smaller number, okay? We don't want to choose a big number for some reasons that I'll show you in a minute, okay? But we will choose some small number like square root of n, okay? So when we use square root of n, we pick that number of features and we try to grow a tree from only those features, okay? So it should remind you of another algorithm that you saw in your deep learning lecture, okay? That algorithm is called dropout. Okay, do you remember dropout? If you remember dropout, please put a yes. If you're not sure, then I'll explain a little bit. So you go to your participants list. Okay. Okay, so why is dropout the right idea? Okay, if you remember dropout, I'm going to just put it here for a second. Okay. Dropout. Okay, just going to write a bunch of ovals here. Just pretend those are neurons for a second. Okay, And what I'm going to do is cross them out, okay, kill them off. Let's say this is a fully connected network, okay? So basically it would be look something like this. You can draw the lines, okay, something like that for all of the layers, okay? So what dropout does is basically tell it to turn off a neuron. It says, sorry, neuron 2 in this layer, you are dead. Okay, you're not working anymore. So I'll take this guy out. Okay, he's gone. I'll take this guy out. He's gone. And then basically all of the edges that touch that particular guy are now off the network. Okay, so I'm left with something like that. Okay, those are the only edges that are left to work on. Okay. Okay, so dropout accomplishes very similar things to feature projection, because if you think about it, if you thought about this as your X layer, okay, this means X1 is on and X3 is on, and I turned off X2 and X4. Okay, so dropout is doing almost the same thing. Okay, it's basically going through your layer and just turning off neurons. Pow, 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 you're dead. Okay, feature projection is doing the same thing. Okay, it's telling the decision tree, turn this guy off. You're not allowed to use it for this particular iteration. Okay, so these are two very different names of algorithms, but are essentially doing exactly the same idea. Okay, if you remember or you've read a little bit about dropout, the idea is that you don't want any one neuron learning too much. You want to spread the information about what it's trying to understand or trying to engineer as a feature over many different nodes. Okay, the same as what we're doing in feature projection, right? We're trying to grow a bunch of different trees. These trees are all going to have different data, and they're, we're not going to trust one tree in specific, but we're going to grow a bunch of different trees that have different viewpoints on the data. Okay. So if you look at the scikit-learn, the sklearn toolkit, you actually see it does this in the choose attribute test in the Python code. And this is a technical hint. Okay. So this is the idea of what we call random subspaces, okay, or feature bagging, attribute bagging, okay. So like I said before, we actually don't want to choose a bag size that's pretty big, okay. Like I told you earlier, we choose, if we have n features, we might choose square root n, okay. Why couldn't we have chose like 9/10 n, okay? Well, I mean, more features is better, right? Because then we get better performance, right? Wrong. And the reason why it's wrong is because of how the decision tree works. Okay, decision tree basically always picks high IG, high information gain features and puts them at the very top, right? So if you happen to have that high IG feature in your data set, you're going to pick it. Okay, so if you have a lot of subspaces that have that feature, they're all going to act the same way at the top. Okay, so that's not very good. Okay, what we want is to get some uh, diversity. Okay, so that's why we don't want to have very highly correlated things. Okay, so if you just did bagging, right? Remember, bagging is this idea of picking instances, right? Even if you turn off some of these instances, right? Okay, those remaining instances are still likely to have the same feature as high information gain. Okay, and that means even though you shot down a couple instances, your engineered decision tree almost looks identical. So doing something like this is not a good recipe for diversity, right? This is why we do random subspaces instead. Okay, so it says right here on the slide, when we sample n prime features, we attend DTL to just that subset of features, right? And we get more diverse hypotheses from there. Okay, so this is this random forest algorithm. You can use this in many different classifiers. You can use it with perceptrons. Okay, that's pretty much dropout. Okay, but maybe slightly different principle, okay? But the whole idea is that we're taking these algorithms and then casting it into different algorithms. So you could use this on Ada Boost, you could use this on Naive Bayes, any algorithm that you want, as long as you want to ensemble it, right? Because if you do this to a normal classifier, it's like, you know, hitting it over the head with something heavy, right? You're basically disabling part of its functionality, okay? That's only okay when you want it to have a different opinion, okay? And you're going to use that as part of an ensemble because you have a diverse set of learners that are looking at the same data set literally from different perspectives, right? Okay, so that is the whole lecture for this week. I like this lecture a lot because I think it's really fun. Um, I don't like the next lecture so much, but never mind. So the bottom line here is diversity is really good. Okay, we want to have a diverse set of attributes in order for us to learn, and a diverse set of instances for us to learn, and a diverse set of models for us to learn, right? So all of these different things are helping in a empirical way. Okay, I won't say they're very well motivated from a theoretical perspective. Okay, and with that, we have 5 minutes to go, so I will turn back to our Ask Me Anything.